Thank you. Thanks for that introduction. Thank you very much. And probably can't live up to that. Yeah, so I'm going to talk just about solar geoengineering or albedo management, or there's a variety of names. And I'm going to actually start by kind of pretty quickly diving into a narrow new technical thing. So those of you who know this well will at least maybe learn something new. We actually even have experiments. Myself and Frank Koich and Jim Anderson at Harvard were trying to push ahead on some atmospheric chemistry. So I'll sort of pretty quickly burrow down to that. But then for those of you who that may be too much for, don't worry, I'll work my way back up. And at the end, I do want to say some things about how I view the sort of big trade-offs between this set of technologies and other things we need to do about climate change, such as cutting emissions and what have you. So without further ado, here goes. So I'm going to assume, so first of all, feel very free, especially a small group like this, feel free to interrupt with the questions or arguments, because I think this topic is a topic that in a way is fun to work on because almost everybody has a strong initial opinion, cab drivers, whoever. And if you think I'm really skipping over something or want to just butt in, feel free to do that. I'm not going to give an explanation at the beginning of what this idea is, because I'm going to assume everybody here will have heard something. Is that pretty fair? So thinking about solar geoengineering, this idea of adding some reflectivity to the planet to offset some of the climate risks. Here's one of the ways I find useful to think about a trade-off between things that you might call the risks, and I'm going to try to define what I mean by this, compared to the efficacy. So any way that humanity might try and increase the reflectivity of the planet is going to have some risks that are particular to the way you do it. So if you put sulfates in the stratosphere, there's some very particular risks, for example, ozone loss. There are other things people talk about doing, painting roofs white, or adding cloud condensation nuclei to marine boundary layer clouds. And each of those things would have a separate set of risks. And then there's the question of no matter how you actually did alter the Earth's albedo, altering the Earth's albedo is not anti-CO2. So it's got, if your goal, and I suppose in principle you can have any goal, but if your goal is to reduce climate risks, then there's a question of how well this thing works to reduce climate risks. So even if you had a perfect way to reduce incoming sunlight by adjusting the sun with a knob, you still don't compensate for all the effects of increased CO2. Indeed, maybe you don't compensate for many, many of them. I'll actually show you something quantitative in this talk about how many you do compensate for. So the way I think about it is of stratospheric sulfates, there are a bunch of particular risks. Stratospheric ozone loss is the first one talked about, the most studied, and we'll get into that in a minute. There's a bunch of related things. So sulfates don't just scatter sunlight, they also absorb infrared, and they absorb a little bit in the UV, and that warms the lower stratosphere, and that's a problem because it will tend to let more water vapor in the stratosphere if you're warming the tropical tropopause region. There's obviously impacts on the troposphere, so any material that you put in the stratosphere, some of it's going to eventually fall out into the troposphere, so you've got to think about health impacts, the particulates or acid rain or what have you. There's these scatterers don't just scatter upwards, they scatter forward. Indeed, for a typical sized sulfate particle, it'll scatter 10 times more forward light than backscattering. So you're going to increase the diffuse light, and that's going to have a bunch of impacts. Whether they're good or bad, it's going to change things in the lower atmosphere, changing photochemistry, changing ecosystems, etc. So these are all essentially risks or problems with the way you might do sulfate geoengineering. And then there's questions about efficacy of any way to do geoengineering, whether it was sulfates or something else, magic mirrors in space or turning down the sun. The question of the extent to which it meaningfully reduces climate change on a regional basis, and I'll get to that later. So I'm going to show you some stuff that is not studying what the risks might be, although we've done lots of that, but actually at this point thinking about specific ways to reduce some of those risks by doing things other than sulfates. So a lot of the ideas go back to ideas, some of which are this is Ed Teller of nuclear weapons fame in 1997, writing a paper that has all sorts of physics of how to put solid particles in the stratosphere. There are all sorts of ideas for solid particles, and it's fair to say that this paper and the next one that I wrote was mostly motivated by the idea that we wanted to have less total mass in the stratosphere. I think because people thought it was somehow important that we spend less money moving stuff to the stratosphere. the more I think all of us think about, the less important that looks. The cost of doing this appears to be laughably low. The issue is risks. And what I'll show you later on is trade-offs between different risks. But in any case, this paper was full of specific ideas about different particles, including ones that could be tailored for their spectral characters or what have you. And this is a paper I wrote that was about levitated particles. And there are a few others of these, but it's fair to say that all these particles, including this is a more recent one that looks at titania, and I'll show you something at the end that shows that this paper was wrong, and actually titania is a lot worse than this paper shows you. But all these papers had basically treated the problem as if you could just put particles in the stratosphere and they'd happily sit there. But in the real stratosphere, they're going to not just sediment out, but they will coagulate. If they run into each other, they'll stick to each other, and they will interact with the background sulfate that's already there, because there's natural sulfate in the stratosphere. And that could actually make the ozone loss problem a lot worse, because as some of you already know, sulfate acts in a variety of ways, but it can act to shift various ozone-depleting substances from their reservoir forms back to their active forms. And if you take the sulfate that's already there and you spread it out in a thin layer on particles, you'll actually increase the surface area with the same amount of sulfate and could make things worse. So that's the sort of motivation for the paper. And the first thing I'll show you is that we've now, Deborah Weisenstein, I, and others have built a pretty serious model. It hasn't, I think, been done before, that allows us to model both the solid particles and their interaction with each other and their interaction with the base liquid particles in a reasonable 2D model that has ozone chemistry. And this is also a little clue for an old paper I wrote, Danny Kirk-Davidoff and co. in Nature, that tried to point out some of the risks of warming the tropical tropopause layer and getting more water vapor in the stratosphere, which has all sorts of problems both for impacting ozone and for warming the planet. So this is our new model. There's an old model from atmospheric research that was, kind of maybe the state-of-the-art two-dimensional model for doing impacts of doing sulfur cycle, and it actually had at some point the best sulfur cycle. And so we've modified that model really in the way I just said. So now instead of just having a prognostic liquid aerosol scheme, it has one for liquids, one for solids, and one for the mixed phase. And it still has all the chemistry, and for what it's worth, it also has the chemistry of the short-lived bromine species, which means that we actually have more ozone loss than typical models have, because most of them don't have that or haven't. So that gives you some sense of what the model is. Now, I'll quickly sort of skip through results and get to these key figures about trade-off that get to what our new ideas. So this is just a little bit of physics of scattering, why you would think about particles other than sulfate. So things that have high index, like alumina or diamond high-density refraction, can be much more effective scatterers per unit volume or per unit mass, and also scatter more of their light forward. So this is a place where we've integrated what's called the upscattering, the average scatter into the up hemisphere. This is the ratio of downscattering to upscattering for sulfate, alumina, and diamond. And basically, alumina and diamond sort of have half as much or less than half as much downscattering for every unit of upscattering. And they're better in terms of mass, but as I'll argue later, mass really isn't the issue here. So this just gives you a sense of the kind of thing we get out of the model. So the model is calculating how particles aggregate. So if we have some kind of monomer, so if we're in the model putting in a monomer that's, say, a 50 micron alumina particle, you'll get the monomers aggregating, and you also can see which fraction are the uncoated and which fraction are the coated, because it's paying attention to how they've interacted with the background sulfate. And we can calculate ozone loss and so on, but now I'm going to go into this trade-off space, which I think is hopefully useful for you to understand, even if you don't have familiarity with atmospheric chemistry much. So here's a trade-off space between the global column ozone loss and the amount of radiative forcing in watts per square meter. So if you wanted to offset some reasonable amount of climate change over the next century, you might want, say, 2 watts per square meter. There's no right answer there. I'll get later on to my views about how to think about what's the right number, but just for the sake of argument, somewhere around 2 watts per square meter might be a useful way to think, though at the beginning a lot less than that. And ideally what you like is something that allowed you to produce this radiative forcing and not lose any ozone. Or maybe you actually prefer to have something that made more ozone. And we'll get there in this talk. But in practice, the actual things that we have destroy ozone pretty effectively. So these are the curves for the sort of standard calculations with sulfate, 2 different versions of the sulfate scheme. And at least in this model, which is exaggerating ozone loss because it's taking today's chlorine loading the stratosphere, if you want 2 watts per square meter, you lose 10% of global column ozone, which is quite a lot. Although the health impacts of that are actually mixed. White-skinned people in the northern hemisphere can be better off with that much less ozone. It's quite complicated. But in any case, here's results from our run with 80 nanometer particles, which are much too small, and I'll just show you an example of how bad things can be. So these particles are too small to scatter effectively, but they're really good for making a lot of surface area of sulfate, so they're really good for destroying ozone. So they basically do nothing in the way of radiative forcing, but they're spectacularly good ozone killers. So this would be a terrible idea. And that's 160 nanometers working our way up, and this is diamond as well. And the point here basically is that by switching to these particles that are solids, now for the first time in a model that's paying attention to the chemistry in a serious way and counting the interactions of particles and counting how many coalesce, we can sort of cut the ozone loss in half for a given radiative forcing. And I think the key thing here is this isn't about money or about the weight of material, unless there's some knock-on effect of that in terms of toxicity, which there might be. It's really about the trade-offs. And there's lots of other axes we could think about here, scattered light and so on, but this is the ozone axis. And the point is we can, it looks like in this model, significantly reduce, a factor of 2, the ozone loss. It gives you a look at the trade-offs overall, and I realize actually the last column of this is old data, and I'll give you a better version. But this is looking at some important quantities. So important quantities are this mass you've got to put up this is millions of tons a year per watt per square meter. The impact on global column ozone, for example, this amount of downward scattered light, and the stratospheric heating, although I'll give you a better version of this so you can kind of ignore it, although the ratios are about right. And so this shows you, for example, that diamond can be much better because it has a high impact and it really doesn't absorb in the infrared. This is now a much more accurate calculation of the temperature change of the troposphere. This turns out to be a lot of work. John Dijkma, who's a research scientist at Harvard, has spent now a lot of time doing this because it turns out that the infrared absorption data for some of these compounds is actually, you can't just go look it up. You've got to go back to these basic oscillator models, and we put a fair amount of work into it. I think one of the surprises is that titanium is actually pretty bad, because it turns out to absorb much more than we expected. But this gives you a sense of, say, these are all normalized to make about a watt per square meter of shortwave, and so say sulfate would increase the temperature of the lower stratosphere by something like 1.5 degrees, which is quite a bit, whereas, say, diamond would basically not have an effect. Maybe all sorts of other problems. So now I want to talk about sort of the new idea, which I've got these adding out of order. A new idea that we've been fooling around with is the idea that you might put on these particles some base, because it's really acids in the stratosphere that are causing ozone loss. So let me sort of talk you through that. The way to think about it is there are 3 acids, nitric acid, HCl, and HBr, that are all reservoir species that interact with their counterparts, which are radicals, NOx, CLOX, and BRX, we call them, which all catalytically destroy ozone, or they also work against each other in interesting ways. So it's not always true that if you have less of these, you have more ozone. Sulfuric acid doesn't itself directly couple to a radical, but sulfuric acid makes an aqueous surface in the stratosphere that itself can take like HCl plus chlorine nitrate and turn it into active chlorine. That's why we've got chlorine losses in stratospheric ozone after Pinatubo, for example. So all these 4 acids would interact with the first 2 columns of the periodic table. And so in principle, if you put something like sodium or calcium in the stratosphere on those particles, you'd make salts. And these salts all turn out to be, well, all the salts we've been looking at turn out to be stable and dry in stratospheric conditions. So NaCl is regular salt, or calcium nitrate, or what have you. And those would tend to remove the acidic species, and then they just rain out in that form. The metals might be metallic, although I think they wouldn't stay metallic. They might be oxides. More likely, they'd be salts with weak acids, which really means they'd be carbonates. So sodium carbonate or calcium carbonate or what have you. And the question is, what if you actually introduced Na or Ca into the stratosphere like this? What would happen? It turns out it's always helpful when you're thinking about these kind of somewhat crazy ideas of some new thing you do to fix a problem we already have, it's comfortable when you find there's already been a lot of work done. So it turns out for sodium, there's already a fair amount of work done, and a lot of the stratospheric models already have sodium in, because there's an input into the mesosphere of sodium from small meteorites. And so there's a fair amount of work on that, and that gives you some sense that we know something about its chemistry, but certainly not I'm not by any means suggesting we know enough to go out and do this in the stratosphere at large scale. We're simply suggesting it's a thing you might want to look at that might be useful for reducing ozone. And preliminary results, we actually now have a bunch more even since this study was made, do show that in this model we can get to a state where if we use solid particles that have some of these bases on them, we can get radiative forcing and actually more ozone than we started with. So pushing it back towards pre-industrial. The ozone has been depleted because of the chlorine that we put there through chlorofluorocarbons. So that's maybe as far as I want to go down this road of like the sort of the cutting edge of what we're doing. And just to be clear, actually I guess there's one more step to go. We're doing lab experiments. So in fact, the really uncertain part of this, it's a really fun part of science where you have a model. So we have Deborah's model now that has a coefficient for how the say HCl might react with these surfaces, but we don't really know the answer. So we're doing a classic flow tube experiment that's the standard way that you measure these reaction rates in the stratosphere to measure that. So we're going to kind of directly bring the lab experiments and the model into conflict in the next, I think, just 2 months probably. So that may be, if you're talking about geoengineering experiments, people often think about things that change the whole world, but this may be one of the few or only examples in the world of an experiment that's focused on a particular geoengineering technology for the stratosphere to reduce risk that we're actually doing in the laboratory. So, circling back up here, I've just talked a little bit, well, I talked about one particular pathway to reduce one of the risks. There's lots of work. I'm happy to answer questions about what the actual risks are. Myself and Steve Barrett and Seb Eastham have done a lot of work, a whole PhD of Seb's, on the health impacts of putting material in the stratosphere. Nobody's ever done that before, and if you think that we're even remotely serious about putting anything in the stratosphere, you've got to do a serious health impact study. So we've run a version of GeosChem, one of the sort of state-of-art lower models of the chemistry of the lower atmosphere, and gone all the way to a health impacts model so we could say something about what the health impacts of putting materials in the stratosphere might be. So just to give you sort of an overview of the kind of work we're doing. So now I want to switch back to this question of how well this whole thing works. And for those of you who maybe that was a blur, you know any stratospheric chemistry, I want you to wake up a little bit. Because what I want to say now is what I think is, if there's a reason to take this whole idea seriously, this is it. It is completely obvious and not disputed that if you warm the world up by putting CO2 in, that you could force the global average surface temperature back to some point like pre-industrial by putting a sufficient amount of pollution in the stratosphere. Because in the end, you can reflect away enough sunlight, you can force the temperature down. But it's not at all obvious whether that in any useful way actually reduces climate risk, because global temperature is just one proxy for climate, but in fact what really matters is region by region changes in precipitation and temperature and soil moisture and so on. So the real question is how well these things actually work on the climate impacts we mostly care about, for example, regional changes in temperature and precip. So this is an example of from a paper of Juan Moreno, Cruz, and Kate Rickey and I a bunch of years ago, where we were running some relatively standard GCM and looking at a bunch of standard regions. So people had sort of cherry-picked before or looked at the global average. This was the first paper to say we're going to use a standard metric of climate impacts. And these are the so-called Georgie regions. They've been used for a lot of climate impact analysis in a whole bunch of papers because they share some climatological similarities. And what we wanted to do was say on those Georgie regions how well or how well it didn't work to do solar geoengineering, in this case with sulfates in the stratosphere in a relatively conventional model, how well it worked to restore the climate. And I'll give you some of that result. Then the way to think about this is the climate response is linear. So if you put twice as much sulfates in, the response you see in a model is pretty linear. And same is roughly true to radiative forcing for CO2. The real world may not be like that, but in some sense here we're comparing model to model anyway, and the real world is probably a lot like that for these small perturbations. So when it's linear, you can think about the following thing. If you had two regions, region A might be temperature in London, and region B might be precipitation in Delhi, or it could be seasonally, just two variables you're picking out of the climate model. If you increase the amount of accumulated CO2, which is unfortunately what we're doing by burning CO2, and we'll have to stop if we want a stable climate, but in doing that, you're going to change these two things by some ratio. This is a dimensionless graph, so it doesn't mean anything, but the point is you're changing them by some ratio. That ratio is basically the ratio of the climate response to CO2-driven radiative forcing in those two variables. And if you did solar geoengineering, which we get to adjust year to year, because the solar geoengineering doesn't last very long. The whole problem with CO2 is it does last long, so even if we stop putting it in, we still have the CO2 in the atmosphere. That will change it in some other way. And so the key thing here is that there's some trade-off. So this is just a drawing, but if you adjust the length of this vector by choosing how much solar radiation management you would do, you can't ever get everything right. So you might make region B exactly right, but leave region A too warm if it was temperature. Or you might try and, if you're an economist, do some quadratic optimal between the two of them, but there's some fundamental trade-off where you can't do both. So the question, of course, is what's that angle? This is just a drawing so far. So I showed you the Georgi regions. There's 22 of them. So if you're looking at temperature and precip, there's 44 dimensions. So you could think of this as like two vectors in 44-dimensional space. But I know that sounds very complicated, but that is the first way people have had to have a clear, not cherry-picking number for how well this technology could work. And that number basically is the angle between the CO2 vector and the solar geoengineering vector. If that angle was 0, then except for its geochemical properties, SRM would be a perfect fix for CO2, because you could reduce everything back to the same point. It isn't 0. If you'd asked me to guess, I would have guessed it was about 45 degrees. I would have guessed that you could, improve things quite a bit, but you'd quickly start making other things worse, and in the mean, you couldn't reduce risks by more than sort of square root 2. The actual answer I found very surprising. It was, to me, the biggest surprise in kind of modeling science out of this work in the last decade. And the actual answer is that the angle for either precip or temperature is of order between a few and 10 degrees, which is equivalent to saying that say for these Georgi regions, you can bring the squared deviation, which is a standard measure of climate impact, of both temperature and precip simultaneously on a region-by-region basis. You can decrease that by like 80% by appropriately choosing the amount of geoengineering. And if there's a single reason to take this seriously, now of course this might not be true, this is just a model result. But if there's a single reason to take seriously the idea that we might actually want to do this, it's that. Because that says that we can really reduce, maybe can, really reduce the climate impacts that we're all actually working on day to day, those of us who work on climate change, a lot. Doesn't mean it's a substitute for CO2. In the end, if you want a stable climate, you have to stop putting CO2 in the air. But it says that there's a potential really big benefit out there to humans and to ecosystems. So you might think that because I'm an advocate that this is just our number and we tweak the number somehow, but this has now been done on the full CMIP-5 ensemble using exactly the same method that we did in that first paper by a range of people, including Alan Robach and co. And bottom line is that new paper, which I'm also an author of, basically got exactly the same answer. So the entire CMIP-5 ensemble produces essentially the same answer, but now you can look at the inter-ensemble differences. So this is, I know, a pretty techie thing. Feel free to ask questions, but I think if you want to boil this down to why should we think about this, why is it worth having a serious research program to look at solar geoengineering, it's that this suggests, but doesn't prove, that you could use it to reduce climate risks, many of the climate risks we normally care about, changes in not just temperature, but in precip and soil moisture, by reduce the risks, if the risks are the quadratic deviation from pre-industrial, which is a standard way to think about risks, going back to Nordhaus, reduce the risks by like 80%. That's a big deal. Might not be true. There might be side effects that make it much worse. It might not be politically controllable. There's all sorts of legitimate reasons you still might not want to do it, even if this is true, but this is the reason to think about it seriously. So now I want to keep kind of going back up to the big picture and talk a little bit about scenarios for implementing. Anybody have any questions about that last result? Because I think it's important. That last result is if there's one thing to take away from this, it might be that. How many of you have seen it before? A little bit. So I think it really is. It's the result that matters, because it's the result that shows there might be something there. And one of the key things is you may have heard the following statement: geoengineering makes the precipitation go down. That is actually not a science statement. The scientifically correct statement is that solar geoengineering, in a sense, makes the precip get closer to pre-industrial relatively more quickly than temperature. So if you choose to bring temperatures back to pre-industrial, which I think is crazy. But if you made that choice, then yes, for sure, the global hydrological cycle goes down. But that's a policy choice. It's not inherent into the science. It's equally true scientifically to say that if you choose to hold global precip constant, the temperature goes up. So people are making policy inferences that are in fact policy inherent implicit assumptions about what is good policy that are unrelated to the core science here. So many of you will have heard that doing solar geoengineering costs precipitation, but it would be just as true to say it increases temperature on the same logic. The underlying fact is simply that trade-off. And what we choose to do about that trade-off is a social choice. The answer might be run away and never use the technology at all, or the answer might be we want to hold precip approximately constant, or temperature approximately constant, or some other variable constant. But this may give you, for some of you who are hearing this for the first time, some insight into the way debate about this has become spun. Because if you Google public documents about this, or many professional papers, and I'll show you one at the end, it's just assumed that solar geoengineering reduces precip, which I hope I've convinced you, if you have any questions, ask me, is not a true statement. It's a true statement to say a particular implementation, which is commonly taken to be solar geoengineering, which I now hope to convince you is foolish, produces precipitation, which is a different statement. Yeah? Yep. So, true. So that same argument could, so two answers. So one answer is if we're talking about the simplest thing, which is just backing up for a second, globally average precip and temperature, then it is a robust result because you can get it out of a column model and you can get it from a few equations. So I think the result I was just arguing, which is that you have a choice of holding global precip constant and increasing temperature, or the reverse, that is robust. Correct. It's about average, and so we've published. There's a paper we published in Journal of Climate Dynamics that actually does the closed loop control and shows this kind of waterbed theorem result, where you actually make the short period noise worse if you make the long period noise less. So that's true, although it's a small difference. And then there's a second thing you're saying, which is you don't trust regional precipitation. And you got to be quantitative about that. I mean, the extreme view of that would be nothing is meaningful about regional precipitation from these models. If you really accept that, then you also can't say that you can't argue for us to reduce CO2 on the basis of these models' claims about regional precipitation. And I think that, I don't know how strong a statement you want to make, but my view is if we're accepting these models' statements about the risks of increasing CO2, we have to assume that the uncertainty is roughly correlated for changes in radiative forcing, unless there's a reason to believe that they behave differently. Well, fair enough. I was pretty careful to say that this is just in this models. So I myself have done lots of work separate from geoengineering on trying to understand the overall uncertainty beyond models. And so I don't think that, to be very clear, I absolutely don't think that the intermodal differences are a good measure of the real uncertainty. But nevertheless, in the same metric that's commonly used to assess all sorts of other climate risks, although I actually think sometimes falsely used, which is these intermodal differences, this looks pretty good. Is that happier? Okay. This is the conversation that I want to have. Yep.
Yeah. So I want to change the conversation with this. So you're not really approaching this from the science, with your science at home, I guess, right? Don't really talking about minimizing the angles, and
Yep.
getting up to 2 to 3 degrees. But in the end, if this is about policy, then there's still going to be winners and losers. And there's still going to be some regions that, even for any non-zero angle, are
Yep.
going to
Absolutely true. Yep.
So to what extent does this really matter, all these angles? As long as they're non-zero, people are going to quarrel about this anyway.
Yes, just like they do for cutting emissions.
Yeah.
Let's get. That's a big set of questions. So I'm not claiming that policy just gets done on this, but on the other hand, ideas about what is global optimum are important in the policy debate. I mean, the whole framing of the core of the IPCC analysis and lots of discussion of climate change for the last, I've been doing 25 years of work on climate, has been anchored around a view of optimal climate policy that's fundamentally a cost-benefit view that says that there are costs to cutting emissions and there are damages from climate and we're somehow going to optimize them on a global basis. I actually don't find that a very convincing guide to my own thinking about climate because I happen to care about the natural world a lot, and so the standard kind of Nordhaus view of climate would say that the reason that I spent 25 years of my life working on climate is to make my kids or great-grandkids 1 or 2% richer, but the truth is I would actually have voted to cut emissions even if it made them poorer. That is, even if the cost of emissions cutting was bigger than the benefits, because I just like to keep the world closer to pre-industrial. Nevertheless, that framing, the framing of some crude understanding of what we think the global utilitarian answer is, I think is relevant to policy, and all I'm doing is using for geoengineering the same thing that has been the dominant thing for 25 years, longer actually, for thinking about CO2. But it has the same weaknesses. And just to really hammer that home, and there are of course losers, both at an individual level and perhaps national level and a corporate level, from any decision to restrain CO2 emissions. So even though most of us, I would guess in this room, think that the winners vastly outweigh the losers, which is why we think CO2 should be cut, if your answer is we somehow can't get to a global agreement because there are some losers, the answer is that's true for any public policy. And the key issue is the difference between the kind of Pareto optimal answer and the optimal answer, that is, how much the worst person gets screwed. And the answer here is surprisingly small. Yep?
So back to the technical aspect. So can you remind us, so the application of the forcing of the stratosphere or the changes
Yep.
in the composition of the stratosphere, is it applied uniformly?
So, good question. So I've shown you quite a few different models that do different things here. So in the model, in the Kate Rickey, well, actually it's about the same answer. For that CMIP5 series, which is from GeoMIP, and from that earlier paper of Juan Moreno Cruz and Kate Rickey and myself, we were doing various versions of sulfates in the stratosphere. But this is sulfates in the stratosphere models that don't truly resolve the size of particles. So they're mostly kind of put in by hand. And typically in a GCM, you get a choice of 1 or 2 modal sizes, a kind of volcanic size or a baseline size. And they've made choices like that. So compared to the earlier model I showed you, stuff from Deborah's 2-dimensional model, which actually it calculates the size distribution itself with a real aerosol model. Most of these GCMs I'm showing you don't do that. So they're putting in a kind of somewhat idealized version of sulfates by hand, not having a real sulfur cycle that's meaningful. They're roughly uniform in space, yes.
Okay. Because that's, I think, another concern, that if geoengineering is applied in a non-uniform way, then you're going to create temperature differentials in the gradients in the troposphere that wouldn't exist otherwise, and then the rainfall is much more sensitive to that conversion.
Yes, that's correct. And there's the flip side of that too, which is said that you have more knobs to control, but those actually could be a bad thing politically because more knobs are actually harder. Yes. More questions? I'm happy with these questions. Okay, I don't have actually that much more to do, but so feel free to interrupt. So I want to think a little bit about scenarios for implementation. And this is part of a paper that is this paper that it was the title of this talk about temporary, responsive, and moderate. So I'm going to start with moderate. And I know some of you may think like even the idea that we talk about this is immoderate, but let me just keep going. So let's say that the benefits in this kind of global optimal sense, which we've just agreed isn't necessarily that convincing, The benefits of solar geoengineering are some function of, say, how much we reduce sunlight for a given amount of CO2. All of this is for a given amount of CO2. It's always true that less CO2 emissions would be good. So this is not a substitute for cutting CO2 emissions. It's something that one could do as well that reduces risk. So in any given amount of concentration or on some trajectory we integrate over time, there's some benefits. And this is just a hand sketch, but actually we have data that looks the same way from a model where we do these squares. So the benefits will first rise because as you just do a tiny bit of geoengineering, almost all climate variables get a little bit closer to pre-industrial. And then they'll peak, and then it'll get worse. And of course, it gets much worse. So there's several papers that show you that if you cut the insulation by 8% for a century, you freeze the oceans back to the equator and you get something like a near-proterozoic snowball Earth, which would obviously destroy all life on land. So that gives you a sense of what the sort of the scope of worst potential outcomes from worst conceivable useless technology is. It's worse than nuclear war. So I'm not trying to minimize that. So that's sort of what it looks like. And then there's some risks. So I was showing you was the benefits. Then there's damages. So these are all the side effects. People don't know those so well, but let's just assume that you can see this is sort of an economist thinking, that the damages go up more quickly than linearly, which is pretty likely true, whether it's ozone loss or what have you. So there's a point here you can think of as peak benefits. Almost all the papers that purport to look at solar geoengineering, its effectiveness, look at the point of peak benefits. The whole GeoMIP system was basically designed around the assumption that we would compensate for temperature completely. And it's very unlikely that that's a sensible thing to do. If you want to use this technology at all, and the answer is maybe we don't, you would certainly want to use less of it, where you have a better ratio of benefits to risks. So just to be clear, I mean, that's a drawing, but there's various numbers you can pull out behind this. This is not making these things up, not making the shape of the curves up. So that's the argument about moderation. It says that if we want to do solar geoengineering at all, we probably want to do quite a lot less than the amount that just maximizes the benefit, because there's damages too. And almost certainly quite a lot less than the amount that holds global surface temperature constant. And that gets back to this thing I was hammering on at the beginning, that people have assumptions about what solar geoengineering is. There are many papers that just make claim assertions. I'll say that at the end. And those assertions are not based on any attempt to find out what would be a good answer. And so in a sense, they're constructing a straw dog and then beating it. That's this paper if you want. So now I want to talk about the phasing through time. So I like these hand-drawn things because it shows you the uncertainty about the future. I've run integrated assessment models. You can produce numbers to many significant digits, but the answer is obvious. If we were in 1900 and trying to predict electricity use or CO2 emissions in the current date, we wouldn't have done very well. So, if you think about gigatons a year of emissions, who knows what business as usual is? It's a counterfactual in a sense we're not in anymore, because people do care about climate and they're restraining their emissions based on climate today. So it's not clear what we mean by business as usual. But if we worked really hard to bring emissions towards zero late this century, you can argue about when, then as you know, bringing emissions towards zero, so that was a figure of emissions, this is a figure of radiative forcing. Bringing emissions to zero basically stops the rise of radiative forcing. Where am I here? So depending on when you start, if you start late, maybe you end up with 6 watts per square meter radiative forcing. If you start early, you end up with 4 or something like that. But more or less radiative forcing stays flat. It actually goes down a little bit, but the impulse response function for climate is much closer to flat, depending on what you think about biospheric feedbacks. So this is telling you something hopefully everyone in this room knows, which is there's a huge inertia, and that what we do, that putting CO2 in the atmosphere basically keeps making things worse, but when you stop doing it, they don't get better. So how to think about solar geo? One common statement, very common statement, is that if you do it at all, you have to do it forever. I don't think that statement is remotely true. That's not there are versions of that are more careful that are true, and it's certainly true that there is a problem where once you do it a lot, you wouldn't want to stop very quickly, but it's not true that you do it forever. So here's an example where if you did solar geoengineering in a way where you ramped it up and ramped it down, say by 2200, some people will say if you don't do it forever, there's no benefit. So Rapier-Humbert makes this argument. And I think he's thinking like a geophysicist, but he's forgetting some human timescales. So it's absolutely true that under this scenario, you haven't made the climate any better in 2200. So whatever you've done to cut emissions has got you whatever CO2 loading you have in 2200. It's got you that climate change, barring some little bit of hysteresis. And this business of geoengineering and then stopping, you haven't made things better. But that doesn't mean you haven't made things better, because you've reduced the rate of change. And there are lots of things that depend on the rate of change. So this isn't a claim about optimality, but it's a claim that there are reasons why you might want to do this temporarily, and there would be real benefits, because there's a host of papers arguing about the rate of change being a risk. The general claim we make in that paper is that any plausible scenario for geoengineering ought to have this property being moderate. It ought to be temporary, and that we ought to be able to think about an endpoint that's not millennia away, that's some reasonable number of human lifetimes away that we can credibly contemplate operating a system for. And any talk about beginning doing this had better have a serious talk about ending it. That is, you've got to have a scenario for how you stop. So you can think about a sort of solar geoengineering wedge, if you like. And now, I said I wouldn't talk about carbon removal, but now we can talk about the combination of them. So if you think again about climate risk, the proxy for radiative forcing, if this was business as usual, and this is everything we do to cut emissions. So in a situation where we brought emissions to zero, so bringing emissions to zero, of course, is just stopping the rise of radiative forcing roughly. Then you can think about how you combine other strategies. So you could add carbon removal. And carbon removal is inherently slow and expensive. If you actually want to remove gigatons of carbon, there's no high leverage the way there is for sulfate in the stratosphere. I mean, sulfate in the stratosphere has lots of things wrong with it, but the reason that you can contemplate it for reasonably low amounts of money is that the ratio of the forcing of a gram of sulfate in the stratosphere roughly offsets a ton of CO2 in the atmosphere in terms of pure radiative forcing, not all climate effects, because there's ocean acidification. But that's 1,000,000 to 1. And so that's the sort of fundamental reason that we can actually contemplate for a reasonable amount of money doing solar geoengineering. Carbon removal is inherently slow and expensive, but you can imagine it as a way to gradually pull the carbon concentration back towards pre-industrial. And then you can think about solar geoengineering as something that you do to cut the peak back, to have less peak of radiative forcing. And then once you're doing that, basically carbon removal is what gets you out of solar geoengineering. So once you've got the carbon removal back to pre-industrial, if that was your goal, then you stop doing solar geoengineering. This may all sound sort of hypothetical, but I think it's important to have a vision of what we might do. And to me, there's one thing that I think is important and positive here, which is that with cutting emissions, which we have to do, all that we achieve is we stop making things worse. With the combination of cutting emissions, solar geoengineering, and carbon geoengineering, you have at least the possibility, not an easy fix and not a quick fix, but you have the possibility of bringing the climate back to something a lot like pre-industrial in sort of 2 human lifetimes. And I think that's a big deal. I think there are ways in which people might be more motivated by a pathway. It's not an easy fix, but a pathway that gets us towards something like pre-industrial in an amount of time scale that's comparably the amount of time scale we've actually done things before as a society. I mean, lots of industrial systems have been around now for more than a century. So that's sort of the core of what I wanted to say about how at least I think about these scenarios. And then I have one last thing where I'm sort of picking on actually a very good friend's paper to kind of show you where I think some of the biases in this field are. But I could take a question or two, or I'll show you these last 2 slides. Yep? I do. Where else would you aim? And if you're aiming anywhere else, are you geoengineering? Why? We don't do that for other biological systems. I grew up in a family of ecologists. I was involved as a kid in helping to do peregrine falcon reintroduction that had been damaged by DDT. We didn't aim just to stop the DDT. We did restoration, and it worked. There are other examples that didn't work, too, to be clear. But in general, there are lots of places in ecology where we aim at restoration. Yeah, that depends on how you adjust the knobs. So one answer is you might decide to hold radiative forcing constant starting pretty soon. That would be a heavier use of solar geoengineering, and you have to, if you wanted to avoid too much CO2, do harder work doing CO2. But I just gave you one example. But if you agree you now have more than one knob, if you think all your knob, the only knob you have is CO2 emissions, and all you can do is stop making the problem worse. If you agree you have more than one knob, then a reasonable answer is you say, actually, we're not going to make radiative forcing much worse than it is now. I'm not saying what the right answer is. I'm saying we need to open up the space of the conversation. I think if you're aiming at something other than pre-industrial, you're basically then saying you're having the conversation about what the optimal climate is. Yep.
Two questions. One is the whole ocean acidification bit.
Uh-huh.
So, what do you do about that?
Stop putting CO2 in the atmosphere.
Well, exactly.
And how is that a question? What's the question?
Well, stop putting CO2 in the atmosphere is the answer. Absolutely the answer.
To the only answer?
I think so.
Lots of complicated problems have more than one answer.
But you're trying to make it more complicated.
No, I'm trying to make the impacts on things I love less.
You're trying to give people an excuse for not doing what they should be doing, which is reducing CO2 emissions.
Why shouldn't people be trying to reduce impacts? Why shouldn't people be trying to reduce impacts?
Well, because you're trying to reduce CO2 emissions so that you don't have the impact.
Well, what's the primary goal? What's your goal?
To make the life on Earth comfortable as it is at the moment.
Okay, so then you got to choose one. You can't choose too many primary goals. So if the primary goal is to reduce impacts, then what I'm doing is not an excuse. It is potentially, with problems, at this point all we should do is study it, a way to further reduce impacts. If you define the goal as reducing CO2, then you've defined away the problem. Then that's easy.
Yeah, what you're doing is you're giving governments or policymakers, whoever it is, a nice excuse. All we can do, all this lovely whiz-bang, clever, flashy science, and we don't have to put our resources, and resources are very limited, into doing something about CO2 emissions. We spend it on clever putting aluminium in the atmosphere.
So let's separate out a couple different things, because this is a great question. So one is separate out what the political and social effects of the knowledge that this could be done are. Then there's a question of what you or I might independently think the goals ought to be. And then there's the last one about costs. Let me just dispense with the last one. So the idea that it's a saw-off on cost is ridiculous. We're now spending globally $300 billion a year on clean energy. And I, and probably you, would like to double or triple that. The total amount of money to do any amount of geoengineering research is about 3 orders of magnitude lower. So there is not a realistic trade-off between the amount of money we're now spending on clean energy, which, as I say, right now is about $400 billion a year, and the amount of money we might spend on geoengineering research or even implementation. So that's the one I think is the least credible. The big thing you're raising, which is credible, but is actually an empirical question, is does the existence of these technologies make it fundamentally harder to get a deal on emissions cuts? And that's an empirical question, and it is not at all clear. Because, so we can try this both at a personal level, and we are doing that actually. Gernot Wagner, the chief economist in environmental defense, and I and Richard Zeckhauser are doing experiments with masses of people where we give them different versions of geoengineering, from Naomi Klein's to mine, give them different knowledge about climate risk, and then essentially ask them a willingness to pay question. And this answer has to do with how people deal with risk compensation. And the answer is, you're sort of assuming one answer, but empirically you're wrong. You get different answers. So if I'm your doctor, if you come into my office and I tell you, you've got a heart condition, you should take Lipitor, the question is, do you then say, if I prescribe Lipitor, do you say, I can just party on, I'm not going to bother to exercise anymore? Or do you actually get a double benefit and both get the risk reduction from the Lipitor, and you now take your heart condition more seriously and do more exercise? And the answer is, different communities of people have different answers. And so in some cases, empirically, we're actually doing this experiment for Lipitor too, in some cases, what happens when you give people a new, potentially risk-reducing technology, you get a double benefit. In other cases, you compensate it all away. And so on a personal level, it is simply wrong, empirically wrong, to say that what happens is compensation. Socially, who knows? It's a collective effect, but I think both things will be in action. And in terms of getting a political deal, I think there are both ways in which the effect you're saying could be right, and I fear it, to be clear. I'm one of the people who's brought this technology visibly forward, and I am terrified that it could have a potentially hideous effect of reducing efforts to cut emissions. But there are also synergies. So I myself have had experience talking to top policymakers and to people on the street who sound like they would be more willing to cut emissions if they thought they had a more complete solution and that they could get more benefits quickly, because cutting emissions does essentially nothing to deal with climate risks to people I actually care about, my kids, because it's too slow. And the combination, doing geoengineering alone doesn't help either, but the combination does something you cannot achieve by just cutting emissions. So I think the bottom line is your fear is right, but empirically it's not true that compensation only goes one way, and practically, in terms of how it plays out politically, we have no idea. And I would challenge you in the opposite. Are you comfortable with the view that we should not research something that has this potential to reduce risks? Because that's the choice. The choice right now isn't implementation. The choice is, do we have a research program? And to date, we basically made a collective decision not to have a research program because of these fears. And the fear is that we look back in 50 years and say, my God, this actually would have significantly reduced risks, and we decide not to do it. So yeah. No, this is the core question. Yep. Exactly. Yeah. But this isn't unique to geoengineering. I mean, the costs of solar have come down by this stunning amount in the last while, largely because of Germany's actions, even though they didn't buy themselves much mitigation. But when people like me, 20 years ago, I've been in people's offices arguing we should cut emissions. That was based on an expected outcome about technological change in energy that made it easier to cut emissions. And so this is not unique to geoengineering, although geoengineering is an extreme case.
Without being an ecologist by training, quite instinctively, I would think that ecology would always want at least intervention.
Yes, but which is at least intervention?
It's a matter of definition.
Precisely. But there's not an empirical answer. So here's the question. Whatever we do to cut emissions, what do you think the CO2 concentration is going to be in 2050? Just name a number. I don't care. What do you think the CO2 concentration will be in 2050? Or what would you like it to be if you were voting?
Well, I think I would rather go for something more realistic rather than something.
Just name a number.
To go now, it won't go down.
So what do you think it'll be in 2050? It's 400 ppm now.
So if we are very aggressive,
Yeah.
I guess it will stay roughly the same. We start
That would be aggressive at the level of killing most of people, but okay, let's say it stays the same. I think that takes a global war to get there, but fair enough. So let's say we do that global war, and it's still about 400 in 2050. Then you still have the question of if the risk is more or less to do with radiative forcing, it is not obvious whether, so your underlying ecological principle is basically we should force the system less. But if you put, say, 1/10 of a watt per square meter of sulfate on top of that, you have less radiative forcing. But then you have this new thing of sulfate. Which version is pushing the system less? It's not clear. To the extent that radiative forcing is a fundamental thing pushing the system, then a little bit of geoengineering is actually pushing the system less. But as I showed, the vector was just looking in a simple way, but of course there's the geochemical effects. It's complicated. The answer is you're pushing it a little differently. They're not perfectly aligned. But the underlying intuition, which is an ecologist would want to push the system less, is surely right, but that actually doesn't answer the question about whether or not you should geoengineer, because by the sort of obvious measures, solar geoengineering is a way you can push the system less. And that's true whatever decision you made about CO2. So whether you did your number of getting to 400 in 2050, or maybe other people might guess that we'll get to more like 450, whichever number it is, it's true that if you do a little solar geoengineering, you, by some measure, are pushing the system less. And by other measures, you're pushing it more because you're doing this new intervention. But what I want to get out here is there's not just saying I want to push the system less actually doesn't answer the question. of whether or not we should do this.
No, I'm thinking about it again, even in small scale engineering, if you want to restore an area, sometimes you do need intervention.
Ecology is filled with interventions. I mean, to go back to my story, how we helped to get peregrine falcons to come back quickly in North America is we engineered it. We had prairie falcons, and we double clutched them. So we put peregrine falcon eggs underneath the prairie falcons, and so we could pull the eggs out of the peregrines and make them have 2 clutches in a season. So we could make a whole bunch of young peregrine chicks, and then we distributed them around North America so we would get the population to rebound quickly. That was the engineered intervention, and there's lots of them like that.
It's just that it's based on much more sort of day-to-day empirical sort of...
True. Yes.
Yeah, so it's a bit less up in the air, literally.
I agree. I don't want to sound like I'm overselling. What I want to do is raise the doubt that simply saying you want to have less intervention, or Joanna's statement that I'm worried about this compensation. Those are both, I don't want to leave you thinking I don't think those are reasonable statements. They're actually really reasonable statements, but they don't actually answer the question of what we should do, because compensation goes both ways. We know this empirically, and there's not an easy answer. Yeah? You can. Okay. Thank you.
Yeah, yes.
Maybe get somebody who hasn't spoken yet.
Yeah, well, I was going to ask how people have responded to the idea of spraying diamonds. US Congress.
Oh, we haven't tried on the U.S. Congress. So the question was about spraying diamonds. So I have no idea. We've just started to do this. I don't think we've tried enough to say.
A more serious question.
Yeah.
In terms of the regional impacts, it seems like one place where this will work so well is the high latitudes.
Well, you can get. You can get a very strong effect of restoring sea ice with these methods in models. Maybe not in reality. You're right that you don't actually reflect away a lot of sunlight in the polar winter, but you reflect away in the summer, and that helps the ice albedo feedback. That's pretty clear both in like even a simple energy balance 2D model, and it's true in a GCM. Yeah, but my view is that to get sort of into the question that we sort of dodged, which is that there's so many huge questions, like how on earth could we ever agree to do this? I think that it gets that while it's tempting is a scientist to add more and more knobs and whistles. I think that if we're going to, it's much easier to imagine a political answer if there's essentially only one knob. So I don't really buy the idea that you try and focus it on the Arctic, but even though I happen myself to like the Arctic and spend a lot of time there. Yep.
I'm a layman, so I'm just curious, you mentioned, it has taken about 20-25 years to reach global consensus for emissions. And so, this is quite a radical idea. How do you think, and how long do you think it will take? Consensus,
Well, so first of all, yeah.
could it be done in your children's lifetime?
So that's also, there's so many good questions. So first of all, we are not at a global consensus about cutting emissions. We're not at a global consensus about anything. That's not how humanity makes decisions. So whether we're talking about control of dangerous biological materials, or central banking, or internet control, or nuclear weapons, the truth is we just don't make decisions by consensus. That's not how the international system works. Maybe some of you wish it would work that way, but that isn't how it works. And for CO2, we absolutely don't have a consensus. I personally would vote to have a very high carbon tax, like hundreds of dollars a ton pretty fast. But that is not what most other my fellow citizens would vote for. So we do not have a consensus about cutting emissions. At this point, we have a kind of dim consensus that it's kind of worth having meetings in Paris and spending a little bit of money. But in my opinion, and maybe in lots of other opinions in this room, the amount of money we're spending is grossly low for cutting emissions. So I don't think we have a meaningful consensus. So on this topic, who knows? Things can go fast and slow. And so you can think of examples where technological change and surprising things happen very quickly and where they're static. In some ways, and Marty Weitzman at Harvard and some others have pointed this out, in some ways it's actually a much easier problem, is an international problem, than cutting emissions. Because the basic problem with cutting emissions is this kind of prisoner's dilemma problem, that each country has to impose upon itself costs where they don't get much of the benefit. If it's true, and it may not be true, that the benefits of this are relatively evenly distributed and the cost is low, then it may be something where it's actually surprisingly easy to get a deal. And you don't need a global deal. You get clubs or coalitions. And there's now been a lot of papers looking at the politics of this that deal with clubs or coalitions. So hard to guess. But on the other hand, for research on this, what we have now is a situation where, despite my arguments, which may or may not have carried any weight with you, that there's something potentially useful here and we should at least look at it, the basic decision in Western democracies has been to not have research programs at all. Is to not have research programs on this topic at all. So we're spending, like the US does not have a research program of any kind. The UK had a little one, now it's near zero. The Chinese just have one, but it's small. But to give you a sense of scale, the targeted spending on this, not compared to emissions cutting, which should be and is 3 or 4 orders of magnitude, 5 orders of magnitude larger. The targeted funding on this compared to all other climate research is a factor of 1,000 roughly, because all climate research, depending on how you count it, is on the US budget it's a few billion a year, and there's no US targeted funds for this. Maybe globally there's a few million. So factor of 1,000. So to me, the outrage is this question of, you've got to be, in my view, really sure that this is either completely ungovernable or it absolutely won't work, to be that confident about maintaining your ignorance about something that's potentially useful. And that's really what we collectively decide to do. And I'm not arguing, to be clear, I'm not arguing that we do this. I'm arguing we get serious about learning more about it, both about the social science questions about how we control it and about how well it would work or not work.
Yeah, kind of answers my question, because I wanted to ask about, at least in climate science and in emissions reduction, we put so much research in it, and we are so clear. At least that the ratio of unknown unknowns, if you want, is probably much lower in emissions reductions than it is in geoengineering. And it means that if we start doing it, we just don't know what's going to happen. So would that not be a really good argument to not do it at all?
I think it's a good argument for research, because research can reduce the unknowns. But I think that argument is both true and not true. So I've done a lot of my work on the energy system, and in fact the unknowns are pretty huge. So I wrote some papers 5 years ago doing nice analysis, I don't think I was biased, about how the learning curve for solar had really flattened out, and about how learning by doing wasn't going to get us cheap solar. In hindsight, we're dead wrong. But I don't think we were biased. That's what the data seemed to show. And then things changed really dramatically for solar PV. It's stunning, really in just 4 or 5 years. And so the energy system, at least in my experience, is really deeply uncertain. I, in my non-geoengineering part of my life, are having big debates about the extent to which batteries are actually needed for grid decarbonization. And there are thoughtful people on both sides who have like order of 10 different answers. So the uncertainty is pretty big in the energy system. And for climate, which is really the issue here, the uncertainties are tightly correlated. So the fact is there are still very big uncertainties about what is the climate sensitivity, about how much the climate will change for a given amount of CO2. And there are, as several people have pointed out, uncertainties about what the climate response would be to geoengineering. But the uncertainty about response to geoengineering and about response to CO2 are pretty correlated, because in what we think of the physics of climate and of the models, which aren't the same thing, those two things look pretty similar. The radiative forcing's a lot of the same uncertainty about feedbacks about upper tropospheric water vapor or clouds or so on apply more or less equally to the response to CO2 and the response to solar geo.
So how could we implement this in practice? And would you
Technically,
get funding from different countries around the world rather than one thing? So that
I'm a scientist, not an implementer. I think technically you could do this in a stupid way in a matter of years. And that's an issue which concerns agencies that are concerned with national security because of the potential for some nation to do that and the need to monitor and know whether or not they were doing it. But we have done studies about the sort of technical lifting costs of putting materials in the stratosphere, and they're pretty low. I think the quickest that I could myself imagine being comfortable doing it would be to start working your way up very slowly with like a 0.1 watt per square meter forcing in sort of a decade and a half from now. But that would only be if you did a whole lot of research now and had a much broader research platform with many more people from many more nations researching, most of whom are actually looking at all the problems and ways it could go wrong. And if after that things still looked more or less the way they did now, then based on what I now know, I might vote to do that slow-moving thing, but I'm just one voter. But technically, there's no, that's what is one of the things that's interesting here. There doesn't seem to be a barrier to starting doing it essentially instantly.
Well, there's some drinks sitting outside, so...
Cool.
I called David's mind to do a podcast.
I'm willing to do that. I'm happy to do a podcast, but for me, I'm actually more, I'll do the podcast because I promised to, but as I said in my response to the email, I'm more excited about having people disagree with me or argue or give me feedback. So, yeah. Thank you.